Okay, time's 9:30, so let's begin here. So for today's class, you need to examine the second of two subsections on forecasting. And again, what forecasting is basically, well, we want to know what the future is going to hold for us in terms of time series analysis. What this means is that we have information up to time point n, and we want to predict what the value for x will be m time points into the future. And the way that we do that is through an intuitive way, and that is we look at, well, what would we expect x at time point n plus m to be given the information up to time point n. So it's just a conditional expectation, similar to what you would see in like a mathematical statistics course. Symbolically, we denote this value as x tilde, and then the superscript we put at n to emphasize we have information up to time point n. And in the subscript, we put n plus m to denote which time point we're actually looking at. And in the previous subsection, we talked about how to get what's called the point estimate. How do I estimate this expected value? Now, in this particular subsection, we discuss confidence intervals. And really the big thing that we had to get a confidence interval for x sub n plus m is to find the variance of the forecast error. So x of n plus m is the true value in the future, and then we subtract off its predicted forecasted value. We try to find the variance of that. And the reason why is because basically we can form this expression here, similar to what you've seen in other stat courses before when you try to find confidence intervals. We have a particular probability that is approximately 1 minus alpha. So alpha is like 0.05. We have a particular probability that has two quantiles from a standard normal distribution in it, one on the left side, one on the right side inside the probability statement. And in the middle, well, what we do is we have the forecast error divide by the estimated variance, the square root of the estimated variance of that forecast error. Once we have that, we can do a little bit of math. So, for example, we move this to that side and to that side. Then we add to both sides this forecasted value. And what do we get? Or what this leads to is the corresponding confidence interval that we need for the forecast. Or that true future value, I should say. That would be a better way to put it. So I can say with 95% confidence that x of n plus m is between a lower number and an upper number from this confidence interval. So what happens then when m gets larger? Meaning that we get farther from where our observed data. What's going to happen to this confidence interval? Does anyone remember? Exactly. We're going to get wider. And the reason being is because if we still want to remain with, let's say, 95% confidence, we have to take into account this, let's say, the fact that we're getting further and further away from what we know the best. You know, this first n time points. And so to still remain at 95% confidence, we need to have a wider interval. And what that basically means is that this variance is going to get larger. It's going to stay the same or get larger. Now, you are responsible for knowing how to derive these corresponding variances. In actual practice, these variances, or I guess the square root of these variances, is automatically given to us by the predict function. Using the variances you get from there and also the forecasted values, we can form these confidence intervals. Then we can do some nice plots of the forecasted values and the corresponding confidence intervals so we can picture what's going on. And lastly, I think this section really helps to demonstrate something that you've seen throughout this course, and that is we use Monte Carlo simulation to help understand these statistical methods better. We do this in this course probably more than many other or most other stat courses. And the reason being is because what I can do is simulate n plus m observations fairly easily, estimate a model to the first n observations, and then look, how well does the forecast do, the predicted values of the future, how well do they do with what we actually observe from our simulation? Also, we can then look at the confidence intervals. Are these true future values that I've simulated, are they within the lower bound and the upper bound of that confidence interval? And so we can see, do our statistical methods work as advertised? And you saw examples of that in the notes. So with that, that's a really brief review. Were there any questions with respect to the material? Okay, let's briefly talk about test number 1. So all of you should have received test number 1 back since we last met. Overall scores, the average score is 90%. The median was 91. High score was 100%. We had 8 students with A's and 4 students with non-A's. Now, if you ended up being a student without an A, of course, I would just want to emphasize, I want everyone in this course to get an A. If you happen to be a student who did not get an A on this test, please go back to the syllabus and see how grades are factored. Remember, your lowest grade for these 2 tests during the regular semester will only be 10% of your overall grade. So if you didn't perform as well as you would like to this time, that's okay. You still have a good chance of getting an A later, as long as you still have a good chance of getting an A for overall your course grade, but you just got to perform better on the next test, okay? Because that next test then would be that 40% of your overall grade, assuming that you're doing higher. Now, if you happen to be one of these students who did get an A on the tests, don't think, good, I don't need to do any more work this semester. So I already got that 40%, that A, that's going to be 40% of my overall grade. Please, please don't do that, okay? Because it's still, you're going to have one test that's going to be 10% of your grade. And, of course, that final exam is worth 20% of your overall grade. And so if you start, let's say, sorry to use this phrase, slacking off now, that will still hurt you in terms of your overall grade for this course. Okay? Now, I hope you've all taken a look at the answer key. The reason why I give you a full answer key to my tests and also projects is because I think that's the ultimate amount of feedback that I can give you. Make sure you look at all parts of the answer key, because even though you receive, let's say, maybe full credit on a particular problem, maybe I had a different way of actually answering it, maybe more concise. Now, by far, the number 1 missed problem on the test was 2D. Dealing with method functions. So this was something that we talked about in class with respect to the class of ACF when we were dealing with the ACF function. Also, if you happen to go through my introduction to R notes, it was also discussed with respect to regression models in the class called LM. Now, in our actual course notes here, we did discuss it relative to the ARIMA function, which happens to be what this particular problem dealt with. The class, though, was a capital A ARIMA. A number of students asked during the test about this particular problem, and I misspoke saying, well, we didn't do this. Well, we did do it. It was just in the estimation section. So sorry, I misspoke there, but we did essentially do it. And so let's take a look at the answer key here. I'll make this a little bit bigger. There we go. So this problem asks, what method functions in R are available for objects created by ARIMA? The first thing that you need to do is understand, well, what's the class that comes about from objects that result from ARIMA? And so this is where that class function comes in. And you can identify that indeed it says ARIMA, just the fact that it's a capital A rather than lowercase a. Now, to find then the actual method functions themselves, the first thing that you need to do is use the methods function. So we say methods class equal ARIMA. And then you have a whole bunch of function names printed. These function names are actually the generic functions. So if you left your answer just like that, where you maybe just did this part here, you didn't get full credit. You needed this extra part right here. The actual method functions are, you take that generic, let's say that stem, you could say, dot, then the method function, then the class for the object. So again, the generic, and then the class. These are the actual method functions. Now, why is this important? Well, this all is very important for a number of different reasons. First, let's say that you wanted to find help associated with doing forecasting in R. If you just did the help, if you look at the help just for predict alone, that's not going to be very helpful because it's going to tell you, it's of a generic function. It's meant for a wide variety of different classes. But you want the help for predict.arima. So what should you do? What you should do is look for the help for predict.arima. That's the approach that you need to take. Also, maybe sometimes, unfortunately, authors of these method functions do not actually then provide the help for the method function, which is quite frustrating. But remember, since everything is always available in R in terms of how the calculations are actually done, what you could do is look at the actual code for predict.arima, and then from that figure out exactly what that function is doing. So this is why it's so important to understand method functions in R. And also, just even outside this class, whenever you're faced with, let's say, using a new model fitting function, one of the first things that you should do after you maybe estimate your model is look at what method functions are available to you so you can understand what else you can do with the results from estimating your model. This is something that I always do whenever I come across something that's new to me, a new let's say, model fitting function. I look at, well, what tools are available to me to do further calculations? And understanding method functions, understanding generic functions are fundamental aspects of using R to get to that point so that you can do this stuff. Are there any questions about that particular problem? Now, something else I want to talk about that's essentially outside this class. And when I went through the ACF stuff in class, I mentioned this before, it appeared to me there was a lot of, let's say, blank stares that you didn't necessarily talk about some of this stuff regarding method functions and generic functions in another class. In particular, I think almost all of you have taken Stat 850. And so as just part of what a department normally does, I was just recently put on a committee that's going to discuss Stat 850 and what material we teach in there. And I was made the chair of that committee. And so I need to know from you right now, do you talk about method functions and generic functions in Stat 850? Yes or no? So we'll take a vote here. Raise your hand if you remember talking about method functions and generic functions in 850. Okay. Raise your hand if you don't remember talking about method functions and generic functions in 850. Okay. So Andrew, you said that you remembered. What was discussed in that?
Well, it was in some of the readings.
Okay.
It talked about it.
I mean,
It wasn't a huge point of emphasis.
Okay. So was it ever, so I believe that the class is taught currently in a flipped format, right?
Yeah.
Was it ever mentioned in person? Okay. It was just something that was in the readings. Were you ever assessed over it, like through a test, a quiz, a homework assignment? Okay. Thank you. That is helpful. And we'll see what happens then with my committee. Okay. So number 3. Number 3 on the tests. Gave you some ACFs, PACFs. You needed to choose particular potential models for this. And there can be multiple answers to these problems. Sometimes I think students were mixing up what tails off and cuts off means. And I've encountered this before in the past for students. Let's just briefly review. Let's say this is an ACF or PACF. The key is when I say tails off, well, that means the values of the ACF or the PACF, let's say, go towards 0. Eventually, you start getting there. Okay, doesn't mean it immediately goes to 0. Just means that it's going towards 0 in terms of these values as a function of the lag. If instead I had cut off, I could have maybe something like this. And notice after lag 2, it's 0. Okay? That is cutoff. Now, what makes things a little bit more difficult is then when we start talking about when we have actual data and we're plotting the estimated ACF or PACF. And we have these dashed lines that go along or go across the plot that help you judge significance. Okay. Still, the tailing off and cutting off that I just mentioned applies here, but you might have something that looks like this. Notice in that cutting off plot, we're having some values that are estimated to be a little bit different from 0, but still, let's say, non-significant. I would still think of this as a case where I have cutting off. I mean, you could even have this a little bit higher, some of these here. And maybe, oops, now I'm down to the line. So I have marginal significance. I would still call this cutting off. Okay? And the same thing here. You might have something that looks like this. I will still see it, say that top plot is tailing off. Again, for emphasis, I want to say that there can be multiple interpretations for some of these plots. It's not always easy to decide when is it cutting off, when is it tailing off, and stuff like that. But what you need to do is try to justify your answer with what is what's given here in terms of the plots. If you feel as though that Perhaps I misinterpreted your response on the test. Please let me know, and I'll take another look at it. Okay, so that's all I have to say about the tests. Overall, scores were good. Okay, it was good to see, but I do want to see everyone get an A on these tests if possible. Any questions? Okay, let's move on and continue talking about project number 3. This is due Thursday, April 4th at 8 p.m. Note that our next Thursday class that we have this week might be a good time to really get going on it with your group members, if you by chance haven't already done that. The project just focuses on forecasting. This is a very important topic of this class. And also, we just kind of got done with, it's a very important topic of this class here. The project itself has less points than normal because it's just focused on one topic, and also because we just got done with that test. And so we've talked about part of it. The stuff that's in yellow we've talked about. The stuff in blue is new. There's a little bit of red typing there too that I will discuss shortly. So problem number 1 here goes back to this earthquakes data. And we want to forecast how many earthquakes we're going to have per year in the future. And so in part A, you estimate an ARIMA 100 mile, in other words, an AR 1 mile. Part B and C, you find these forecasted values for 3 time points into the future, or time points 1, 2, and 3, I should say. Then part D says, okay, now let's find that standard deviation of the forecast error. In other words, again, you're finding the square root of the estimated variance of this. Okay. Use the predict function. That, of course, will be the easiest way to do these calculations. But I think it would be very good for you to is see if you can do this essentially by hand, by using the expressions that we have for the estimated variance. I'm 95% confident. For some reason, I'm not 100% confident right now, but I'm 95% confident that in the notes we do an AR1 example. And so we do have the actual expressions in there, so you don't actually need to derive it for this particular case. Just go through that as extra practice, because maybe on a test I might have you do that. Also, I want you to make sure that you use the proper notation when stating these values. So don't just, run predict and, the values are given. Actually state the values with the proper notation, like the estimated variance part, or the square root of the estimated variance. So you probably will need to use the equation editor to set this up. And, the reason why I want you to do this is because, you need to understand what proper notation is. It's like almost learning a foreign language. You have to be able to express what something is symbolically so that other people, eventually when you get outside this class, other people outside this class would know exactly what you mean. Then with these estimated standard deviations, find the confidence interval for m equal 1, 2, and 3. So not too difficult of a calculation. Then I think what I guess is one of the more fun parts then in this class is, okay, let's do a plot of our data. Plot the observed data, plot the forecasts. Then plot the corresponding confidence intervals for m equal 1, 2, and 3. Note that on this particular problem, I didn't ask you to find the predicted values for time points 1 through n, so you don't have to do it, even though obviously in the notes I do that a number of times. But plot the observed data, plot the forecasted values, plot the corresponding confidence intervals. And then lastly, I think is a good overall question. Suppose you are a seismologist. So you deal with earthquakes. And you're being interviewed by the news media for a video that's meant to go to the general public. Maybe it's going to be on like a newspaper website or something. And they ask you, how many earthquakes will occur next year? Well, provide a response to this question with an appropriate explanation. But make sure you take into account, this is the part in red, make sure you take into account that the audience for this interview, so people who are going to view this video, primarily are those without a statistical background. So you need to state what you think is going to happen. State it in a way that a non-stat audience can understand it. This is something that you will be faced with, whether you're a statistician or not a statistician, you'll be faced with outside this class. Not just necessarily for time series analysis, but for other places as well. That you often will need to explain stuff to people who don't know what a confidence interval is, or they don't know what an ARIMA model is. How can you state that? How can you communicate with them so they have an understanding of what's going on? Your response doesn't have to be too long, maybe a paragraph. I think I did it in, now I don't remember. I think I did it probably about in 3 sentences. Also, what's motivating this particular question is something that I told you that kind of motivated me even introducing this data set to you. And that is, every year, right about when hurricane season starts, we always, if you follow the news media, you always hear some kind of prediction, some kind of forecast about how many hurricanes will be in the Atlantic Ocean this year. And, when I came across this earthquakes data set, that made me think, I bet someone would want to do the same thing with earthquakes too. Any questions about this problem? Okay, so problem number 2. So to do these confidence intervals for the forecasts, we can't just have predict alone doesn't automatically produce these confidence intervals, which is kind of too bad. You have to do a little bit of work on your own. It's not that difficult, but you do have to do a little bit of more work on your own. So how about you construct a function that will automatically always give me the confidence intervals, or give you the confidence intervals, rather than always having to rerun the same kind of code over and over again to do the calculations. Write one function that will automatically give you the confidence intervals. So in this function, there should be 3 arguments. 1, something that gives you the model fit from ARIMA. 2, how many time points do you want to go into the future? And what I'm envisioning here is that, let's say if m was 3, you want time point 1, 2, and 3. It would be kind of strange to think that, well, I guess it depends upon the application. It would be kind of strange that, oh yeah, I only want 10 time points in the future. I don't care what happens at time points 1 through 9 in the future. I don't care about those. That would be very strange for most applications. There might be some justification once we get to seasonal models. And also, one could choose, and also you have alpha. Okay? So, write a function that does this. So with, and then run it on what we just did in problem number 1 and verify you got the correct results. Many times outside of this class for other applications, you will need to do other stuff like this, where you would have to rerun the same, let's say, 10 lines of code over and over and over again to do something. And one of the beautiful aspects of R is that you can just write your own function that will do it, so that instead, you could just use one line of code in the future always to do those same kinds of calculations. And so this just gives you some experience with doing this. And then lastly, for number 3, now we're going to get to some derivations. For an ARMA 2.1 model, or ARIMA 2.01 model, part A, find the forecasts for m equal 1 and 2, derive it. And then now part B, find that variance of the forecast there. Write out the formal derivation. Okay, so that is project number 3. Any questions? Okay, we got basically 2 more things to do. The first thing is going to be really short. So Econ 920. So Mike Ricks, who is a fairly new assistant professor in the Department of Economics, contacted me a week or 2 ago to tell me about his course that he's teaching over there that might be of interest to statistics students, especially those who are taking time series analysis. His course is his course deals with applied econometrics, which basically means we're using statistical methods to do the stuff that one wants to do in economics, with an emphasis on implementing design-based causal inference. So causal inference is a topic that's been around for a very long time, and over about the last 10 or so years has become a hot topic in statistics itself, which basically is focused on understanding, rather than how, let's say, one variable is associated with another variable, we're interested in determining, is this variable causing the results from this variable? It is a slightly different meaning. And we don't have a course on causal inference in our department. And so this might be something that might be of interest to some of you. It's going to be in spring 2025. Mike gave me some additional information about the course, and I'll post that after our class to my discussion board. One thing that he hopes to be doing is to do some kind of flipped or blended learning format for the course. And just in general, if you this department often has courses that students from the Department of Statistics will often find interesting, especially those who find time series analysis of interest. You can think of time series analysis as a subset of econometrics. Econometrics is much larger, though. And again, econometrics is basically using statistics to do various things that are of interest in economics. And so beyond Econ 920, you might want to take a look at some of their courses. I know I haven't looked in the last couple of years, but I know that they used to have at least like Econometrics 1, Econometrics 2, Econometrics 3 as an actual courses. And just in general, also, before you take a course outside of your major, please make sure you always talk to the instructor of that course first. Because very often, it's just meant for their students in that major, and you want to make sure that you do have a sufficient background that's needed to succeed in that course. So don't just go into the course blindly that first day without you ever talking to the instructor. Also, your advisor and actually your supervisory committee has a final say-so for whether or not you can use a course as part of, let's say, your memorandum of courses or your program of study, so that you can actually count it towards your degree. So you should always talk to your advisor too. This is especially the case because, unfortunately, statistics instruction at UNL is kind of decentralized to some respect because the Department of Statistics is not that old. And so I know there are, I know Econ used to have like a Intro to Econometrics course, which was basically just a regression course that, at least in the past, we in the Department of Statistics would not allow our students to take because it was something else that they would have already had in one of our courses. So make sure you always talk to your advisor or your committee to get their approval. Okay. Now let's talk about the main last thing that we're going to do today. We're going to go back to this COVID-19 pandemic data, this wastewater data. And, the big picture here, why are we looking at this data? Well, first of all, it's kind of a topic of current interest. But also it helps to reinforce some of the stuff that we've done elsewhere in this course. It gives us some more experience working with some of this material. And also allows us to look at some stuff that maybe I don't have necessarily enough time to put it into my videos or my notes that would be of interest. And that would be important to know. The stuff that I'm going to do here today is going to be put into my COVIDwastewater.R program. So there's, again, a picture of the data that we've seen. And where we left off last time when we looked at this data, we thought that perhaps a log transformation of X at T would be appropriate to deal with some non-stationarity issues with the variance. And maybe an ARIMA 100 model might be an appropriate model for the data. So what should we do next? Well, if we have this model, we can put into practice what we've just learned in our forecasting section or subsection. And so that's what we're going to do next. So here I'm going to actually estimate my model once again. We've done this before. Now, because of how R works, notice how I can simply log transform my data right inside the function called to ARIMA. And here we go. So, for example, phi hat 1 would be positive 0.87. Okay, so now we're going to do the forecast. And again, this should be review. I use the predict function. My model fit information is in mod.fit. I want to go 3 time points ahead. And also I want the standard errors, in other words, the standard deviations of the estimated variance of the forecast errors to be calculated. So I put a true there. And this is what I get right here. So in terms of the general object type here, just as a review, what's returned to us for 4.mod? What general object type? Not looking at the class of the model, the class of the object. What's the general object type? It is a list. Thank you. And the reason why I know that is because notice I have a $pred. I have a $SE there. Now, this is getting to more how R works. Notice that mod.fit is also a list, but returns a different look to it. Why did that occur? This is a more, I think it's a more advanced understanding of how R works. Why do you think mod.fit didn't give me, let's say, mod.fit $coefficients? Because I know that exists, or coef, excuse me. If maybe this might help you to understand it. So notice if I did names 4.mod, I have 2 components to the list. And when I printed off, I'll just go back down. When I printed off 4.mod, notice it gave me the first component, then it gave me the second component. But when I printed off mod.fit, even though there's a mod.fit $coef, there's a mod.fit $sigma 2, it did not print off in a similar manner to 4.mod. And one of the words that I use there is kind of a key word to understand. It did not print off the same. So what's going on here? Why did R react differently? I will say the default for printing whenever you have a list, is to do exactly what we did with 4.mod. So whenever you type an object at a R prompt here, a particular function is always run. What function is it? Print. It will always be run. Print is a generic function. Now we saw from the test that for a class of arima, there is a print.arima function. And so what R is going to do is going to look when mod.fit is implemented like that. We don't have to put print first. It will automatically always implement print. But we'll try to find the class of mod.fit. It sees it's arima. And we'll look to see, is there a print.arima function? If there is, it will run it. And so there is print.arima. Okay. Now, .mod has a class of list. And let's see here. There actually is not a print.list. So does anyone know what method function will be run in this case then? It's okay if you don't know, but these are important topics to understand. I wish I could type right. It will run something called print.default. So in R, if R cannot find a method function corresponding to a class of an object when you type a generic function, it will, if it can't find that method function, it will go to what's called a default method function, print.default. Another example that we've seen before, for example, is plot.default. Even though I've never mentioned plot.default before, but there's actually a plot.default as well. And so that's how R's working here. And so what will happen then for the default is it will just simply list out all the different components, their values. We'll try this. I don't think I've ever tried this. Let's see what happens if I did print.default mod.fit. So I'm telling R, hey, don't go to that print.arima. Go to print.default. Let's see what happens. There you go. It printed everything that's in that list. Just like what we saw with 4.mod. Okay. Any questions? So next, what I like to do is actually find the corresponding confidence intervals for the forecast. So I just simply pull out the forecast, subtract off the quantile from the standard normal, times then I pull out the standard errors. I have a subtract here, I have a plus here. You put it into a nice data frame to print it off nicely. And there we go. So for the first week, this is weekly data, for the first week into the future, my forecasted value is 13.27 to 15.08. Okay. 95% confident that the true value is somewhere between those two values. So let's now do a plot. So I use plot, and the way I'm going to do the plot is I'm going to specify an x-axis value and a y-axis value here for this case. So I'm going to go 1 to n. The length of x is n. Y-axis, log of x. And so notice also here for my x-axis limit, this is always something important to do whenever you want to put the forecast on your plot. You need to make sure that the forecasts fit. So you need to make sure you extend out your x-axis a little extra to account for those forecasts. So I say I'm going to start at 1 and go to the length of x plus 3, n plus 3. And here's my plot. I'm going to put the corresponding points on the plots as well using my points function. And there's my original data. So now to do the forecast. Excuse me. What I decided to do here was to actually include the predicted values too. You don't, depending upon what you want to do, you may or may not want to do it. And so to get the predicted values on there, I use log of x minus mod.fit $residuals. You know, why am I doing that? Well, we can, and this isn't covered in the notes, but it's good to review. You know, think about what a residual is. And just like regular old regression, you know, often we denote a residual by the letter E. So E for error. So if the residual is E is equal to, let's say, your response variable Y minus the predicted value Y hat, right? Now, I could rewrite this so that I put Y hat on the left side, and now on the right side, I'm also going to put E. So if I take Y minus E. So if I somehow know what Y is, well, I will know what Y is. If I somehow know my residual as well, I have a quick and dirty little way to get to my Y hats. And so that's essentially what I did here. Here's what equivalently what my Y would be. It's the log of x. Here's the equivalent of what my residuals are, mod.fit $residuals. And so that will give me my predicted values for time points 1 through n. And then I combine that with those 3 forecasted values in the future. Now, for my x-axis, I need to go from 1 to n plus 3. So I have n plus 3 different values I'm actually plotting on my y-axis. And I can, you know, choose some various like plotting characters, 17 and so on. And here are the corresponding predicted values and then the forecasts in the future. I can add my my confidence intervals as well. I'm only going to do, of course, the confidence intervals for m equal 1, 2, and 3. So remember how low contains my lower bound, up contains the upper bound. I'm going to be plotting at n plus 1, 2, as in TO, n plus 3. And here are my confidence intervals. And this is what I get. Okay, so what will often happen when you do a plot like this and include those confidence intervals will get left off, at least partially, or might be partially. And so if you notice, my upper bound of my confidence interval is kind of cut off. And we don't want that to happen because, after all, what's the purpose of doing this plot? We want to see the entire confidence interval. So just as a note that you should always watch out for, you will often need to adjust your y-axis. There's a few different ways that we can do this. Let's see here. One way is just by, the simplest way is just by visual inspection. Maybe I can start at 10. Maybe I'll go up to 16. It probably will work. There are fancier ways that you can do it, such as making sure you got the minimum and the maximum for your data, and also your forecasts are included. So if I redo this plot with my y-axis limits now set, I should be able to capture everything on my plot, and indeed I do there. Okay. Excuse me. If I wanted to, I could also, on my x-axis, put the actual dates. I decided just to do this more quickly, not fool around with dates, and I just left it as the time index. Okay. So here's a question for you. So we got a lot of stuff going on in this plot. Why would it be helpful to zoom in? Well, I guess I kind of already answered the question. We got a lot of stuff going on in this plot. It's really, I have to admit, it's kind of hard to see, to some respect, what some of these forecasts are, confidence intervals are, and how the predicted worked with the compared to what was observed. And so very often, whenever you do one of these plots, you produce a plot like this, and then you produce a second plot where you zoom in on all the forecasts and maybe some of the most recent time points observed. And so how can we do that? This is a little bit different way than what we did in the notes. I just create an object called zoom, where I'm going to zoom in for n minus 10 all the way up to time point n in terms of, maybe I shouldn't use the word zoom there. I'm just looking at let's say about the last, I guess this would be last 11 time points that were observed. And then I'm going to adjust my x-axis to make sure it goes out 3 time points into the future. So I create this index that helps me zoom in. And so we can see those are the time points in there. Then for my plot, now my x-axis, I'm going to plot just those zoom in indexes. Notice how I extract those from x themselves. I just look at that time index inside of x, still put that within the log. And I make sure that my x-axis limits are properly adjusted. So I start at the beginning of my zoom, and then I end at zoom plus 3. And so now there's my observed data zoomed in. Next, I plot my forecasts, or the predicted values and the forecast. So notice here when I put the predicted values in there, I just choose the corresponding indices that correspond to time point n minus 10 up to time point n. I add to it my forecast in terms of add to the vector. And there we have that. And so now this is a little bit less, it's a little bit easier to see what's going on compared to what we had before. I can go ahead and add my confidence intervals like before as well. And this is what we get. And so again, I think both plots typically should always be given in an analysis. Any questions? Okay, then I guess I have some questions for you then. Well, we already talked about number 1 here. What is an intuitive reason for why the confidence interval bands or bounds, confidence interval limits, confidence interval limits get wider as m increases? Well, we're looking at up to 3 weeks into the future, and so we have less certainty about what's going on. So in order to still remain 95% confident, we need to have a wider confidence interval. Why does the forecast, and hopefully you noticed this in some of the stuff that was in the notes, whenever you look at one of these plots, it looks like the forecasts are a little bit behind. Well, do you think, well, let me ask you this. Do you think the forecasts are a little bit behind here in trying to get at those, excuse me, I didn't say that right. Why does it look like the predicted values for time points 1 through n, why does it seem like they look a little bit behind in terms of what the actual observed values are? So what do I mean by behind? Let's start here. Look where my mouse is. I'm at this point here for the observed data, and then I go up to my observed data, then I go up to my observed data again, and notice how it takes a while, or it takes, in this case, just one time point. Here's my predicted value, and then similar to how I went up, again, watch my mouse, I went up here, notice how I'm going up there. Notice how I go up here, and I go up there. Why does that occur? Seems like it's behind. It's just trying to give you an intuitive understanding of what's going on here. We have an autoregressive 1 model. Okay, 1. And so the way that again, I don't have it up here, but you think about how that forecast looks. It takes one time point for the forecast to take into account what changes have been made. And so that's why that's occurring. There's nothing to be alarmed about, but this is the best that we can do. So, third question. These are forecasts for the log of x of t only. Of course, we want it for just x of t itself. So what should we do? How do we get the forecast now for x of t? Should not be a difficult question to answer. How should we get the forecast now for x of t? Yeah, use the exponential function. Okay. Now, when one does that, whenever you have transformed data and you're doing your model on transformed data, and then you need to transform back to the original data scale, sometimes weird things can happen. Okay. And at least the way that project number 4 is written in the future, I forecast that you will find some weird things that may happen. So, all I need to do is use the exponential function, right? Uh-oh, that doesn't work. Well, we have to take into account what's actually inside of 4.mod. It's a list. It has 2 components. The exp function does not know how to work with a list that has 2 different components to it. So instead, what you're going to need to do is take each component separately and apply the exp function. Okay. So if I want to get my now confidence intervals for the future values, all I need to do is apply the exp function to that low object and also to the up object. And there's my confidence intervals. Now, I could do one of these forecast plots. And in actuality, this is the main thing that we want. We probably even, let's say if you're doing an analysis yourself, or maybe you're doing an analysis for someone else, you probably wouldn't have even shown the plots that we just looked at because it was on the log scale. We would probably be just focused on just the original data scale itself. So we need to do this on the original data scale. So I do my plot of my observed data, much like what we've done all semester long. And there's that plot that we've seen. Now, to get the forecasts and the corresponding confidence intervals, I just appropriately applied the EXP function. You can look at the details on your own. And this is what I get. Again, the black, and I should put a legend there. Shame on me. I did not put a legend on these plots. You should always put a legend. I apologize. You can see the black triangles towards the end are the forecasts. The green dashed lines are the confidence intervals. Let's zoom in. Well, first of all, we just look at that first. Let's just do that. What characteristic about these confidence intervals is unappealing? Look how wide they are. If you tell someone, okay, for next week, I think the amount of virus that we're going to have in our wastewater is somewhere between here and there. They're going to be like, whoa, that's a really large range. Why do you think it's so large? Think of intuitive reasons here with some basic statistical reasoning. Let's think of it this way. In order to get a wide confidence interval, what needs to typically happen? If you're going to fix, let's say, at 95%, you're going to need to have a large variance. Okay. So we have a large variance here. Why do we have a large variance? Look how much variability we have in our data. Look at that, where my mouse is. That's probably why things are so wide. Let's zoom in. And that's what the zoomed in version looks like. Something else that's kind of interesting. Notice that the interval is not symmetric around the forecasted value. Why is that? When we originally constructed those intervals, we did plus or minus value from the standard normal distribution times the square root of the estimated variance. So you would expect it to be symmetric. But at least the intervals that we have here are not symmetric about the, I'm sorry, I shouldn't use the word symmetric. They are not equal distance. The limits are not equal distance from the forecasted values. Why is that? Yeah. So this is an unintended side effect. That because we had that transformation, that's what causes the intervals to look like this. Now, what can sometimes happen, too, depending upon the kind of transformation that you have, and depending upon the actual kind of data that you have, maybe, again, depending upon that information, maybe this limit might be below 0. And let's say that you have data that can only be greater than 0. That's not very appealing to have. But depending upon the transformation that you're working with and the actual data that you're of interest, you can have those unappealing things happen. And something like that might happen on project number 4. Okay, so I think then the last thing that we're going to do is that, we have a unique aspect to this data. And that is, let's actually look at the data again. I first was putting together these examples with in a couple weeks before school started, or this semester started, and so I had information up to January 6, 2024. Now, obviously, now we're towards the end of March, so now we have a way to check how well these forecasts actually perform. And so this code will give you print out the forecast and stuff, and I just copied and pasted that from R into here. And so for week of January 13th, the forecasted value was, let's see, 1.43 million. The confidence interval was about 580,000 to 3.5 million. What was the actual value? Well, it was observed to be 1 million. You can look at some of these other ones too. 1.2 million was the actual, 1.2 million was the forecasted value. The confidence interval was 370,000 to 4 million. Notice how that's getting wider. And you can look at, I guess, time point 3, which is January 27th on your own. Let's compare the forecast first. So the forecast for January 13th was 1.4 million. It was 1 million. So we're off by roughly about 40%. Then for week 2, 1.2, it was actually 630,000. So we're off by a lot as well. Our forecast was double what the what it actually was. But take a look at the confidence interval, because those forecasts, we know that there's going to be variability there. We don't expect them to be perfect. That's why we form confidence intervals, why we want to say we're 95% confident that this actual true value, let's say January 13th, is between two numbers. So we can check, did the confidence interval work? 1 million, look at this. It actually fits inside the confidence interval. 630,000, it fits inside the confidence interval. So the confidence intervals did work as we would like them to. So on one hand, I'm a little bit disappointed, in terms of how much variability that we have in our data. It's somewhat hard to predict. But at least these statistical methods are showing that once we take into account that variability, I can still capture what that true value is. Okay. Any questions? So, at least I think it's a nice little application of something that's, I guess, a current event topic. I guess one other little thing you can think about is that, should we use this model to predict for next week? Well, I wouldn't. It's too far in the future. Let's get as much information that we have. Maybe update this model for up to now, then forecast next week. That's the way in other applications would be done in actual practice. Okay. So let's talk about what's next in our class. So today I'll be available for questions after class. Do note that, again, the Department of Statistics is interviewing this week, and I have a seminar to get to at 11:30 a.m. So I can answer some questions, but I do need to leave here by 11:15. You do have a quiz that's due on Canvas today at 8 p.m. On Thursday, I'll have my usual office hours. We'll have the help class again. And if you haven't started working on your project with your group, this would be a great time to start doing that. Next Tuesday, office hours at 8:30 again. We'll have our regular class. You have two subsections to examine. The first one excuse me, deals with what's called a drift term. This is something that I think I didn't first start teaching until the last time I taught this course. It's something that you don't typically see taught too much, but the last couple editions of our book they decided to put that in there, and I thought, okay, that's kind of an interesting topic, and so that's why I've added it. And you'll see what happens with this thing called the drift term. Now, subsection 13 is the first of two subsections that talk about something called model building. In other words, we're going to put together a lot of stuff that we've talked about this semester, and then also add a little bit more information to it, so that, let's say you're given a data set and you want to figure out what is the best model to use with that data set. How do you do that? Well, we've seen some tools that help us determine models, if a model is good or not. Well, we're going to go through a whole model building process that, again, combines some stuff that we've talked about with some additional stuff that we're going to do. So like if you've in a course that you've had on regression analysis, you typically see what's called what's done a residual analysis to check, are your model assumptions violated or not, or if changes need to be made to your model. Well, we're going to perform a residual analysis now with our time series model, and if we find that there are problems detected with the model we've chosen, this residual analysis will show us where to go next. How can I change my model to make it better? This material corresponds to section 3.7 of our book, if you're reading that as well. Any project questions, we'll handle those as well. And then you'll have a quiz that's due next Tuesday too. Project is due Thursday, April 4th. And looking farther ahead, test number 2 is almost about 1 month from today. So April 25th. Any last questions? Okay, then that's all here for today.